Real quick, I want to tell you about what happens if you get obsessed about gravity and you worry about it in intimate detail. So the first quick story has to do with Henry Cavendish, who wanted to know the average density of planet Earth. Why? Well, it had to do with wondering how the Earth got made. And in order to do this, Cavendish honed an apparatus developed by a friend of his, John Mitchell, that used some cannonballs. Well, actually, there weren't cannonballs. These balls in his apparatus were 350 pounds each. And they were attracting the small balls of a dumbbell suspended from a thin fiber. So he brought up the balls to cause a twisting in one direction, and then he moved the balls around to the opposite way to cause a twisting in the opposite direction. And from this, and very careful work at age 67, he found that the Earth was 5.48 times the density of water. The modern value is 5.52, so he did a pretty darn credible job. You can do this experiment in our sophomore lab, as it turns out, to about 1%. And it's pretty impressive because the force between the masses in our experiment is down at the nanonewton level. And yet you can read them out. I'm going to skip this one. When I was a postdoc, I was down in the basement at Gila in Boulder, Colorado, and I kept hearing something going off, and it was this guy's apparatus to measure G very carefully. And the basic idea is that you keep dropping a corner cube and you look for the interference from a laser between the falling cube, which reflects the beam directly back, and a reference one that's in a suspended state to isolate it. And you do that a bunch of times and you measure G. Well, how accurate is it? It was accurate enough that in Boulder, Colorado, he could tell if there was a Pacific storm that was crashing on the shore of the West Coast. So we've approximated so far that the Earth is a sphere, and so it would gravitate as though all the mass were at the center. That was that important point about the theorem of Newton. But the Earth is not a sphere, and it rotates. So if you want to be more accurate, as a function of the latitude, you have these small corrections to take into account because the Earth bulges around the waist and rotates, throws you away from the axis of rotation. And it can be very useful to investigate exactly how gravity varies over the surface of the Earth. Oops, that was supposed to be a movie. Hang on, let's see if we can get that to work. So it's a little difficult to read the times here, but these are measurements that are made by the GRACE Gravity Recovery and Climate Experiment pair of satellites. There are two satellites that are up in an orbit that goes over the poles, and so watches the Earth spin underneath it. And they're about 200 kilometers apart. They constantly beam a signal back and forth between one another, and they're constantly talking to the GPS system, so they know really very well where they are. And if the front satellite comes to a region near the Earth's crust that's particularly dense, then it will be especially attracted, and it will speed up and move away from the rear satellite. And by watching that distance, they can then map out what's happening on gravity underneath. Well, imagine, and so what you're seeing here is that when it rains, the gravity goes up, because now you've got extra mass, and then as it dries out, so this little movie demonstrates that you can watch hydrology by using a satellite that's running around, measuring very accurately the distance between these two satellites. And some of their work is used to try to understand the rate at which the polar ice regions are melting. Okay, any questions? All right.